Hello, everyone. Welcome. I'm Jet Aguilar from the Astronomical League of the Philippines, and I will be your host for today's webinar. Thank you so much for joining us, which will be for our eighth webinar for the Astronomical League of the Philippines Astronomy Experts Speaker Series. And I am happy to see a lot of registrants attending not only from the Philippines, but from other countries as well. And I would like to thank this opportunity again for all of us who joined our past 7 webinars with attendees coming from around the world in countries like the United States, Canada, Puerto Rico, United Kingdom, Germany, Denmark, Greece, Japan, United Arab Emirates, New Zealand, Singapore, Malaysia, Indonesia, Cambodia, and Nepal, among others. About a week ago, it was headlined in Philippine news that the Philippines has lost US $10 billion due to climate change. And true enough, the effects of climate change is real, and it is already having huge impacts on vulnerable countries like the Philippines. Today, we are very fortunate to have with us a world-renowned expert on climate change to speak on this very important and timely topic. And he will talk on the topic of, the title of his talk will be on Turning the Telescope Back to Earth, the challenges of living on a warming planet. And my fellow ALP member, Ms. Imelda Joson, will be introducing our speaker. For those who are not able to register, but would still want to watch this webinar, we are currently live streaming on Facebook at the Facebook page of Philippine Astronomy Forum. And before we start the lecture, allow me to explain some rules for this webinar to help us make this an enjoyable learning experience for all. Please listen and do your best to give your undivided attention to our speaker. There will be a short question and answer session at the end of the lecture. You may type in your questions under the Q&A tab found in your Zoom interface at any point during the presentation. We will do our best to read and answer your questions live after the lecture via the Q&A tab. We would like to remind everyone that the contents presented in this webinar will remain as the individual property of the lecturer and the photographers in the presentation. We will be distributing certificates of attendance via email to all registered attendees who will be present with us throughout the webinar. So please use the name you have written in your registration forms to help us facilitate this process. So enjoy the webinar and have fun learning. And this is the program flow for today. And I would like to turn you over now to Mr. James Kevin T., the President of the Astronomical League of the Philippines, to give his welcome remarks.
Good evening to our viewers in the Philippines, and good evening to our guests in the United States and Europe. My name is James Kevin T., President of Astronomical League of the Philippines. On behalf of the ALP, I would like to welcome you to our Astronomy Expert Speaker Series. This webinar is part of the ALP's International Astronomy Education Outreach Program. Our goal is to bring renowned experts and scientists to the Filipino people and to the rest of the world. That is why the webinar is being offered free to the general public. I would like to take this opportunity also to thank our ALP members who has been instrumental in putting up this program altogether, especially Imelda Joson, Edwin Aguirre, Dr. Jet Aguilar, Jun Lau, Kendrick Colty, Andrew Ian Chan, and Peter Benedict Tubalinal. So this is the 8th lecture in our speaker series. The first one was given by Professor J. Pasakoff of William College. and it was followed by Mr. Zolt Levay of the Space Telescope Science Institute. And it was followed by Mr. Joe Rayo, then Mr. Eclipse himself, Fred Espenac, then followed by Robert Reeves, then Ken Crawford, and the last one, which is the astronomy editor, David Aker. Our speaker for today is Professor Mathew Barlow, a professor of climate science from the University of Massachusetts, Lowell. We have more distinguished speakers lined up for the upcoming months, so please stay tuned and please do not forget to register in advance for these future webinars. Thank you very much, and I'd like to turn over the program to Edwin Aguirre, who will introduce the guest speaker for today.
Hi, everyone. It is my distinct pleasure to introduce to you today our guest speaker, Professor Mathew Barlow. Professor Barlow is a climate scientist at the University of Massachusetts Lowell. He is a world-recognized expert on climate variability and climate change, particularly extreme weather events such as heat waves, droughts, extreme rainfalls, and floods in locations ranging from the northeastern United States to the Middle East. Professor Barlow was one of the lead authors in the 2021 United Nations Intergovernmental Panel on Climate Change, IPCC, 6th Assessment Report. His research has been supported by the U.S. National Science Foundation, the National Oceanic and Atmospheric Administration, NOAA, and NASA. He has contributed to more than 60 papers in scientific journals, including Science, Nature, and the Proceedings of the National Academy of Sciences. He received his PhD in meteorology from the University of Maryland, College Park in 1999, and he joined the faculty of the University of Massachusetts Lowell in 2005. Ladies and gentlemen, please welcome Professor Matt Barlow.
I'd just like to thank everyone for this opportunity to speak to you. This is a real honor for me, and I'm delighted to speak to you on what is, I think, a very important topic. So this is a talk to astronomers, people interested in astronomy and astronomers. So I'm going to talk about climate change a little bit more here from the perspective of astronomy and planetary science. So Earth is a planet in many ways like any other planet. So we can think about it with the tools of astronomy as well. So here's what I'm going to talk about today. So this is climate change for the astronomically inclined. So we're going to talk a little bit in general about what determines the surface temperature of a planet. Probably spend most of our time working our way through that because the general science of surface temperatures of planets of all planets is really covers the main pieces that we need to understand climate change on our own planet. So we'll talk about what the factors that determine the surface temperature of a planet, and then we'll more specifically apply that to Earth. So what are the implications of that science for human-caused climate change? And then end by talking a little bit about what that looks like for the Philippines in particular. And I want to end with a little bit of a discussion of what we can do about it, and is there a cause for hope? This is a very difficult topic in many ways and has had devastating impacts many places around the world, including the Philippines. So I think it's important to think about what we can do going forward rather than getting completely bogged down in despair, which is all too easy. All right, so to begin, let's think about how we can figure out the surface temperature of a planet, any planet. And let's start by asking, how can we figure out the surface temperature of a planet that we haven't visited? So from the point of view of measuring with astronomy, how can we figure out how hot a temperature is? We're looking at a temperature, another planet in our own solar system or planets elsewhere. So one of the main principles in figuring that out, two main principles I'll introduce. So the first one is that the hotter something is, the more energy it emits. And if you're a fan of physical laws, that's known as the Stefan-Boltzmann law. But the main thing is the principle. The hotter something is, the more energy it emits, and the wavelength of the energy it's putting out depends on the temperature. That's Planck's law. So just to review, apologies here, this is a little bit of a busy schematic, but I wanted to introduce what kind of energy we're talking about, because there are lots of different types of energy. So the energy emitted by an object because it's hot is electromagnetic radiation. And everybody is familiar with at least some pieces of electromagnetic radiation, some types of electromagnetic radiation. And maybe the most familiar is visible light. So this schematic here, this diagram is showing you all the types of electromagnetic radiation. And the x-axis here is wavelength. So we have really short waves over on the left-hand side, really long waves on the right-hand side. And for this type of energy, really short waves also have a lot of energy. They're high energy. Really long waves are relatively low energy. So we have visible light is probably the most familiar type of electromagnetic radiation, but everything here is actually the same thing as light. It's the same phenomenon as light, just at different wavelengths. So gamma rays and X-rays are also the same thing as light. They're just shorter waves and higher energy. Ultraviolet and then visible. So we have high energy waves that are shorter than light, and then we have all these lower energy waves that are longer than light. So infrared, microwaves, radio waves. So there are lots of things that seem very different, I think, to most of us, like radio waves and X-rays and light. We don't often necessarily think of as the same type of thing, but they are. They're all the same type of thing, just at different wavelengths. So those are that's the type of energy that objects emit all the time, and how much they emit and what wavelength they emit depends on their temperature. So to make that a little more concrete, why can we see the sun? So here's a picture of the sun from the International Space Station. Why can we see the sun? We can see the sun because it's so hot that it emits visible light. So our eyes have evolved to see in the visible range because the sun is putting out so much energy in that range. And the surface temperature of the sun's about 6,000 degrees Kelvin. So very, very hot. Things that are that hot emit white light. But there are also other things that most people are probably familiar with that also emit light. So here are this is a picture of campfire coals at night. Very hot metal also emits light. And the temperature of the coals here is about 1,000 degrees Kelvin, so much cooler than the surface of the sun. And although they're still emitting energy, they're still emitting light in the visible wavelength. Notice that it's a different color. Now we're looking at reds and some yellows instead of whites. So we can actually estimate the temperature of a remote object, something we don't have to touch it, we just need to see it, we just need to get the light from it. And the temperature of that light, the color of that light actually tells you the temperature of the object. And this is a little table telling you that around 1,000 degrees Kelvin, like the coals, it's going to be red. As we get more like 6,000 degrees Kelvin, like the surface of the sun, it's going to be white. So we can actually get information about the temperature of an object from a distance. All right, what about cooler objects, things that are not red hot, like things that aren't on fire, things that aren't like the sun? What about like a dog? This cute little dog here. So this is a picture of a dog, and just to explicitly acknowledge it, this is a picture of a dog in a well-lit room. So we can also ask, is this dog, which is more like 300 degrees Kelvin, so it's much colder, is this dog also emitting visible light? And in order to figure that out, we'd have to turn the lights off and see if it's emitting any visible light, and it's not. Dogs, people, the atmosphere, anything that's more like 300 degrees Kelvin does not emit visible light. But it does emit one of the other wavelengths of light. It emits infrared, which is a longer wavelength than visible light. And you may have seen these pictures with infrared cameras, sometimes called thermal imaging cameras. You may have seen these with movies or people with night vision goggles. And the way that those work is that those types of cameras or those types of imaging devices pick up these longer wavelengths of light, that infrared light. So it turns out that all objects, again, all objects are emitting electromagnetic energy. It's just if they're really hot, like the sun, they're emitting in the visible. But if they're cooler, they're still emitting light. They're still emitting electromagnetic radiation, but just at longer wavelengths that we can't see. So we can actually measure the temperature of pretty much anything as long as we can record the amount of light, of electromagnetic energy it's putting out. To be precise, and we'll come back to why this is important in a little bit, to be precise, objects are actually emitting at all wavelengths, not just a single wavelength, but they emit most of their energy in a narrow range of wavelengths. So we're focusing here on the wavelength where the object is emitting the most energy. So for example, the maximum energy emitted by the sun is in the visible light, but it does also emit some energy in the shorter waves and in the longer waves. So this diagram here is sort of similar to the one that we saw before. So the x-axis here is wavelength with really short waves on the left and really long waves on the right. This red curve is how much energy the sun is emitting. So the sun is emitting the most energy here, medium amounts here, and basically none at the very short and the very long wavelengths. And this rainbow in the middle is just showing you where the visible light range is. So the sun is emitting most of its energy in the visible light range, but it is also emitting energy in the ultraviolet and in the infrared. So our main work zone, the main types of electromagnetic energy, the main types of light that we're interested in terms of most stars and most planets is in the visible for the stars because they're very hot, and in the infrared for many, not all planets, but most planets are emitting in the infrared in these longer wavelengths. So as shorthand, we typically refer to visible light in this context as shortwave radiation. And we typically refer to the infrared, the longer wavelengths as IR, short for infrared, or long wave. So unfortunately, climate science and is as prone to this as any other science, we often have many terms that refer to the same thing. I'll try to be a little careful here, but shortwave is visible light and long wave is infrared. And then just to give you another kind of more concrete example of this, when I say many stars are emitting in the visible, just think if you go outside at night or any kind of visible astronomy that you do. If you go outside at night, you see millions and millions of stars. Because you can see them, that means they're emitting in the visible spectrum. So with careful imaging, we can actually estimate the temperature of those stars just by the light that we're receiving from them. And the same thing from planets. So this relationship between how much energy something gives off and the temperature it has is how we get information about temperatures and surface temperatures of planets and stars without having to actually go there. So in terms of astronomical measurements. So to get back to our original question, how can we know the surface temperature of a planet without visiting? careful measurement of electromagnetic radiation, light, at a range of wavelengths can give a lot of information about the surface temperature of a planet and what the atmosphere is made of. All right, so all of that is kind of backstory. That's how you can actually measure the surface temperature of a planet. But what determines the surface temperature? Why does it have the surface temperature that it does? And this is where we start to get into the science that's really relevant for climate change. So surface temperatures in the simplest cases for planets is just an energy balance. Energy in equals energy out. So in the simplest case, the energy in, the way that a planet gets energy, is solar energy, energy from the local star. And the way that planets typically lose energy is just this radiation, this emission of infrared or long wave energy. So if we have a little picture here of a planet, we have energy coming in from the sun, and we have energy going out because the planet is hot and it radiates energy. One thing that we have to account for is that all planets reflect at least some of the sunlight, of the solar energy that's coming in, and we need to account for that. So if you see diagrams like this, it often says absorbed sunlight or net sunlight, and that just means accounting for how much of that sunlight is reflected without being absorbed by the planet system. Some planets are very highly reflective, like Venus. Some planets hardly reflect at all, they're very dark, and some planets are somewhere in between. And it's also maybe worth pointing out that the reflectivity, how much of that energy is reflected, can change over time for a planet. So Earth right now is reflecting about 30% of the sunlight that hits it, but it's been closer to 80% at some times in Earth's history. So that number is not fixed. That amount of reflection, it can depend on what's going on the planet's surface. So if we can estimate the output of energy from a star, which we can do a pretty good job of just by looking at the light that it's putting out, if we know the distance of the planet from the star and the amount of reflection, we now have enough information to estimate the temperature of the planet, just from a few very basic pieces of information that are relatively easy to measure. All right. That brings us to our first sort of wrinkle and our first mention of a term that you hear in climate change all the time, the greenhouse effect. But we're going to start here with the natural greenhouse effect. So we often hear the greenhouse effect in reference to the human-caused greenhouse effect. But there is a greenhouse effect that occurs naturally and is very important to planetary atmospheres. So the key is that an atmosphere that can interact with the infrared radiation that the planet is putting out will absorb some of that energy coming up from the surface and re-emit it back down. So this is a little cartoon of a planet without an atmosphere. And then this is a cartoon of a planet with an atmosphere, the little blue ring around it. And if there's no atmosphere, the planet just loses its energy to space. But if there is an atmosphere that can absorb, that can interact with infrared radiation, as the energy is going up from the planet, some of that is absorbed by the atmosphere and re-emitted back down, making the surface warmer. So if the atmosphere is absorbing some of that upward radiation and re-emitting it back down, that's basically an additional source of energy to the surface, so it becomes warmer. So this is known as the greenhouse effect. The fact that you have an atmosphere, if it can absorb infrared radiation, it re-emits some of that radiation back down after it's absorbed it and makes the surface warmer. This is the greenhouse effect. This is the natural greenhouse effect. Perfectly general, nothing to do with people, happens on many planets. Venus would be a great example, as we'll see. Nothing people related about it, just a basic property of atmospheres and planets. So I've said a couple times an atmosphere that can interact with infrared radiation. So not all gases strongly interact with this kind of radiation. So a gas that can interact with infrared radiation is called a greenhouse gas. So it's possible for a planet to have an atmosphere that is not made up of the type of gases that interact strongly. And in that case, the atmosphere doesn't provide much of a greenhouse gas. So it makes a difference what your atmosphere is made of. So because many of you are probably really familiar with some of these ideas, but many of you may not be. So I just wanted to give a little more information about that kind of an argument. So this is a little schematic of the surface of a planet and the energy going into and out of the planet. So this is about the simplest case you can have. There's energy coming in from the local star, usually in the visible range. And then there's energy lost from the planet because it's hot, it's radiating energy like all objects do. So you're losing energy to space. In the simple case, they're balanced. The amount of energy coming in is equal to the energy going out. And in the case of no atmosphere, it's really this simple. And you can directly figure out what the surface temperature of such a planet has to be if you know the basics about the planet. And it will be that simple. So in this case, think, say, Mercury. But if a planet has a greenhouse atmosphere, things are more interesting. So this gray area is now the atmosphere. So we still, for these planets, have the same amount of energy coming in from the local star. You have the same amount of energy being lost to space. You have the same balance if you're looking at the edge of the planetary system, because you still have energy coming in and energy going out. There's no new source of energy in this case, but because you have an atmosphere, it's essentially redirecting the energy within the planetary system. So with a greenhouse gas atmosphere, you have energy going up into the atmosphere, but rather than being able to go directly into space, some of that upward energy is absorbed by the atmosphere and re-emitted back down. Okay, the fun part. We sort of thought about all of these things. Let's actually apply it to a few examples. So the key thing to keep in mind, the temperature that we calculate, thinking about these energy principles, the temperature that we calculate is for basically the outer edge of the planet. If there's no atmosphere, the outer edge of the planet is just the surface of the planet. So if there is an atmosphere, the outer edge is actually the top of the atmosphere. So the temperature we calculate by seeing how this energy is coming into and out of the planetary system, we calculate the same temperature every time, but it can mean something different if there's an atmosphere. So we calculate the temperature, and then we measure the surface temperature of the planet. If those two temperatures are the same, it means there's no atmosphere. If those two temperatures are different, we know that there has to be an atmosphere. So without sort of going into the math of it, here are some of those calculations for our inner planets. So we have our 4 planets in our solar system, in our neighborhood. These are the temperatures that we calculate based on these energy principles on what energy is going in and what energy is going out. And then these are the surface temperatures that we measure for the planet. So you can see, take Mercury, for instance. Mercury, from energy, just tracking where the energy is coming and going, we know that the temperature of the planet has to be about 440 degrees Kelvin. If we actually measure the surface temperature of Mercury by looking at the energy that's coming out of it, we get 440 degrees Kelvin. We get the same number. So we know that the edge of the planet that it's emitting from is just its surface, because these numbers are the same. So the greenhouse effect is 0. Let's skip over Venus and Earth for a minute and look at Mars. So for Mars, the temperature that we calculate based on energy principles is 210 degrees Kelvin. The surface temperature that we measure for Mars is about 218, so it's a little warmer. So we know that there must be at least a little bit of greenhouse gas atmosphere. There must be at least a little bit of an atmosphere that absorbs infrared on Mars, because it's making it about 8 degrees warmer than it would be if we took away the atmosphere. All right, let's look at Venus, which is sort of the king of greenhouse atmospheres, at least for our solar system. So just in terms of energy balance, the temperature of the outer edge of the planet, the top of the atmosphere, is 228 degrees Kelvin. The surface temperature of Venus is 735 degrees Kelvin. The surface temperature of Venus is crazy hot. So the effect of Venus's atmosphere is 507 degrees Kelvin. There's a huge greenhouse effect on Venus. If you took away Venus's atmosphere and looked at the surface temperature without it, without the atmosphere, it would be vastly colder. So Venus has a huge greenhouse effect. And again, this is the natural greenhouse effect that we're talking about here. We tend to hear it mostly in terms of climate change, so we tend to make this association in our head between the greenhouse effect and human causes, but there are no human causes on Venus or on Mars. This is all naturally occurring greenhouse effect. All right, and then Earth. So Earth, from an energy balance perspective, the edge of the Earth system from an energy balance perspective is about 255 degrees. The surface temperature for Earth is about 288 degrees Kelvin. So we know that there must be an atmosphere from Earth. If you were looking at Earth from another planet, if you were looking at Earth as an alien visiting by, you would make exactly the same conclusions without actually having to visit Earth. So we know that Earth has must have a greenhouse gas atmosphere, and it's having a pretty substantial effect. So our atmosphere on Earth is making it about 33 degrees Kelvin warmer than it would otherwise be. So another way of thinking about that is that without our naturally occurring greenhouse gases on Earth, Earth would be permanently frozen. So the natural greenhouse gas effect from the point of view of mammals like ourselves, from the point of view of the ecosystem, it's really important to us that Earth have a greenhouse atmosphere, because otherwise Earth would be permanently frozen and not livable to people. So the naturally occurring greenhouse gas effect is very positive. And the two main naturally occurring greenhouse gases in the atmosphere are water vapor and carbon dioxide. And if you follow climate change, one of those will really leap out at you, which is carbon dioxide. So carbon dioxide naturally occurs in our atmosphere. We appreciate the fact that it naturally occurs because it's part of keeping the planet at a livably warm temperature. But that's a gas also that human activities emit a lot of, primarily through the burning of fossil fuel. So that's the carbon dioxide, the CO2 that you always hear about in terms of climate change, because not only is it naturally occurring, but we're substantially increasing it through human activities. And not a little bit, we've already increased it more than 30%. So we're taking something that's a natural property, a natural important part of the physical system, and we're increasing it a lot. All right, so I'm going to say a few things about how controversial or not this science is, because some of this isn't widely known. So it's always fair to ask with a scientific result or a scientific theory, how well tested are these ideas? And the ideas that I've presented to you so far are actually very old, very long settled science. So almost everything I've talked about so far is the science of the 1800s. So the warming effect of an atmosphere, the fact that if you have a greenhouse atmosphere, the surface temperature of a planet is warmer, that's been known since the 1820s. It's nothing particular to climate change. It's just a basic property of planets. the identification of the first greenhouse gases, water vapor and carbon dioxide, that came in the 1860s. And calling them greenhouse gases is actually from this time period as well. So this language of calling it a greenhouse, calling it greenhouse gases, that all predates concerns about climate change. But people were well aware for a very long time that we're emitting carbon dioxide as part of fossil fuel burnings, as part of the Industrial Revolution. So the first calculation of the effect of doubling the amount of carbon dioxide, something that we still talk about today, that actually is pre the 1900s. That was first talked about in the 1890s because people have had some concerns about our influence on the amount of carbon dioxide for probably more than 150 years now, almost not that long after we began emitting them, because this is basic science. Greenhouse gases, the greenhouse effect, very basic science that we've known for a long time. And the first measurement of the greenhouse effect for Venus is from the 1950s. So, you know, again, this is very basic theory. It's theory for planetary sciences, just for understanding the world around us. And people had been suspecting for a long time that the atmosphere on Venus was very important, very dense, and very important for surface temperatures. So the first measurement of that is quite old as well. So these ideas that I've talked about so far, the basics of greenhouse gases and the greenhouse effect are very old and very well tested. All right, so what are the implications of this kind of basic planetary science, this kind of basic astronomy? What are the implications now for human-caused climate changes? And again, climate change is often painted as controversial, so I want to say a little bit more about that before we move on. So I think it's kind of a fair question. If this is basic science that's relevant to all planets and all stars, why does it seem like there's so much controversy about it? So a little bit less the last few years, depending on where you look, but we've heard a lot about how controversial climate change is. And the only reason, there's very little scientific controversy about climate change. But you wouldn't know that from what you read on the internet or what you read in the paper. The reason that you hear about controversy is because the fossil fuel industry is making a ton of money off of burning fossil fuels. So the fossil fuel industry makes about $3 billion every single day, more or less for the last 50 years or so. So this is a tremendous industry invested in producing greenhouse gases. And this fossil fuel industry has invested heavily in promoting doubt about climate change science. So the controversy is not in the science itself, but there's been this promotion of doubt about the science. And this isn't my opinion or conspiracy theory or anything. This is extensively well documented. There are a ton of research papers, there are a ton of documents that have been found by the fossil fuel companies showing that this really is something that they spend a lot of money on. And there are entire books written about this, maybe the most readable of which is a book called The Merchants of Doubt, which you can Google and easily find, which really walks you through this heavily funded disinformation campaign. So from a climate science perspective, it's almost confusing because climate scientists regard this all as very basic, well understood old science, and not controversial. Okay, so with that in mind, what does all of this mean for climate change, human-caused climate change? So the basic science of climate change is very simple. If we increase greenhouse gases, it's going to warm the surface of the planet. That's a very basic physical fact for any planet. This will cause sea levels to rise, both due to the melting of ice into the ocean as it gets warmer, and the fact that a warming ocean expands. So not only will the surface temperature of the planet get warmer, but this will also cause sea levels to rise. And also rainfall will become more intense because a warming atmosphere can hold more water. So climate change is not just warming surface temperatures, but also sea level rise and more intense rainfall, which probably for anybody in the Philippines or any island nation, I think people are probably very well aware of it. I, again, just want to emphasize that these basic aspects of climate change have been understood, modeled in climate models, and predicted since the 1970s, and have been clearly observed, have been seen to occur since the 1990s. So these basic aspects are rock solid. We're completely confident in these pieces of climate change. There are also many other effects: shifting of rainfall pattern, shifting of ocean currents, shifting in the seasons, that would be a whole other long talk, so I won't get into them, but I do want to acknowledge that I'm highlighting here kind of the biggest, most basic impacts, but there are a lot of other impacts, which from a planetary science perspective is utterly unsurprising, since we're changing a basic property of the planet. We're changing what is in the atmosphere of the planet. So we shouldn't be surprised that the climate changes pretty dramatically. All right, so that's just a high-level overview of the implication of greenhouse gases for climate change. So more specifically, what does that look like for the Philippines? And before I dive into that, I want to acknowledge very explicitly where the carbon dioxide we currently have in our atmosphere comes from. So this big box here with all the colors, this is the total amount of carbon dioxide in the atmosphere. And then all the individual boxes are where that came from in terms of different countries. And the colors are different regions. So the reds are all the carbon dioxide that's been emitted from Asia, greens are North America, oranges are Europe, Africa, South America, and Oceania. So I just want to acknowledge that, be very clear that climate change is now everybody's problem, but it wasn't caused by everybody equally. And you can see that some parts of the world, like Africa and South America and Oceania, have contributed very little, whereas Asia, Europe, and North America have contributed a lot, much more. And I'm speaking to you as a US citizen from the US, speaking to a lot of folks in the Philippines. So just to highlight those two countries, the US has been the biggest emitter of carbon dioxide. So the biggest source of the problem is the US, which I'm a part of, and the Philippines has been a very small player. So when we talk about impacts of climate change, I think it's important to acknowledge who caused those impacts, who's responsible for them. All right, so the Philippines, probably as many of you are aware, are expected to be one of the most impacted countries, unfortunately. As an island country in the West Pacific, which is very prone to typhoons, it is one of the most vulnerable countries. There are a very wide range of impacts from climate change in the Philippines. And I'm going to point you in a minute to two different reports, because it's not possible to cover all of the impacts quickly. But some of the worst are sea level rise, which has a lot of different impacts, some of which are very obvious when there are storms, some of which are less obvious. Like the higher the sea level is near the coast, the more salt water penetrates inland and pollutes freshwater. So freshwater aquifers are influenced by sea level rise, just as one of many examples. So sea level rise stronger typhoons, which I'll say more about in a minute, higher temperatures, of course, and not just the highest temperatures, which unfortunately we make it already, and this will get worse, harder to even work outside. But there are also lots of human-made systems, cooling systems that fail at higher temperatures. So there are even some non-obvious impacts of higher temperatures. Economists used to assume that as long as you had a building with air conditioning, higher temperatures didn't make any difference at all. But around the world, we've seen that cooling systems for buildings can fail fairly easily. You have things like nuclear reactors, which can't run if it gets hot enough outside because their cooling system doesn't work. So higher temperatures really affect a wide variety of things. And then again, for the Philippines, damage to marine resources as the ocean gets hotter. The ocean is also getting more acidic because when carbon dioxide goes into the atmosphere, most of that then goes into the ocean and makes the ocean more acidic. So the ocean is getting hotter and more acidic, which is very bad for corals. It's very bad for many fisheries. It's very bad for coastal water quality, for algal blooms. And this, of course, is terrible news for everybody, but particularly for island nations. So this, I realize, very difficult to process list of impacts is why Philippines is one of the most vulnerable countries to climate change. Again, despite the fact that the Philippines bear very little responsibility for producing the pollution that's caused this. So 2 QR codes here, or you can just Google them. I'm also happy to make this the PDF of this presentation available. So there are national reports that go into much more detail on the climate impacts of the Philippines. So this is a link to one of those. And then there are also international reports that provide less detail, but much of a bigger picture. So this is the Intergovernmental Panel for Climate Change, or IPCC. So this is a report that includes information on the Philippines with a lot more detail. I'm just kind of giving you the big picture here, but there are big efforts to provide a lot more detail, how much these will continue to change in the future, and critically, how much we can restrict the change, how much we can make the change less worse by taking action. All right, I wanted to mention typhoons specifically, both because they're important in the Philippines and because they're important everywhere, actually, or almost everywhere. So as you may know, typhoons are a type of storm called a tropical cyclone. Typhoons are just strong tropical cyclones. And one thing that's a little confusing around the world when we talk about these storms, about strong tropical cyclones, excuse me, is that they have different names in different parts of the world. So in the US, we tend to call them hurricanes, but hurricanes and typhoons are exactly the same thing. And in other parts of the world, like the Southern Indian Ocean, they just call them cyclones. But they're all exactly the same type of storm, a strong tropical cyclone. And this type of storm is strongly affected by climate change, because with climate change, we're warming both the ocean and the atmosphere. If you have a warmer ocean, you can have more evaporation into the atmosphere. If you have a warmer atmosphere, the atmosphere can hold more water. So when you're providing all that extra water into an atmosphere that can then hold more of it, you're going to get much heavier rainfall. The other part of it, which I don't have time to get into too much detail here, but when precipitation happens, when rainfall happens, it's water condensing from a gas into a liquid. And that's actually a tremendous release of heat into the atmosphere. So the evaporation from the ocean in the atmosphere is also the fuel that drives tropical cyclones. So the more evaporation you get, not only the more rainfall do you get, but you get a stronger storm as well, because you're providing more fuel. Water is basically the fuel for tropical cyclones. So climate change is providing kind of a twofer, doubly impacting these storms, making these storms not only rain harder, but also making them stronger. And a third factor, because we have sea level rise, any storm surge associated with the storm, with the tropical cyclone, is occurring on top of an already higher ocean. I also wanted to sort of connect the dots. Just in the last 10 days or so, we've had extreme flooding events from 3 different tropical cyclones in 3 different parts of the world. A typhoon hit Japan last week, causing massive flooding and damage. A former typhoon, typhoons can change into different types of storms as they go north, called a post-tropical storm, but they're still very strong. So a former typhoon actually made it all the way to Alaska and caused massive flooding in Western Alaska. Then we had a hurricane just a few days later, Hurricane Fiona, which devastated Puerto Rico, which still hasn't recovered from the last major hurricane there, Hurricane Maria. And then this storm, Hurricane Fiona, which devastated Puerto Rico and then impacted several other islands, actually just made landfall last night in Nova Scotia in Atlantic Canada, and is possibly going to be the strongest storm ever for Canada. So just in the last 10 days, we've had this outbreak of tropical cyclone impacts all over the Northern Hemisphere. Just in the last 10 days, it's really remarkable. And this isn't an accident. Climate change is supercharging these storms. So these storms, typhoons, of course, very, very important for the Philippines, which sees so many of them, but also important for very other large parts of the world. So I'm going to try to wrap up in a few minutes. This is a big topic. I just also wanted to point out that heavy rainfall is becoming more extreme in general, which is something that the IPCC looked at in a fair amount of detail. So not just tropical storms, but also winter storms, thunderstorms. Heavy rain in general is becoming more extreme over most parts of the world. Monsoon rains, like in Pakistan this summer, are becoming more intense than they used to be. So this is just a link to a general audience piece that provides an introduction to the increase in heavy rainfall and the overall intensifying of the water cycle. All right, so I want to wrap up. So I just want to end with, is there cause for hope? So this is all pretty dire. These are all extremely devastating impacts. What can we do about it? And is there any hope that we will actually do anything about it? So I just want to mention 2 things fairly quickly. One is the ozone hole, which isn't in the news so much anymore because the international community got together and did something about it. So ozone depleting chemicals were a major environmental issue in the 1980s. There were a lot of concerns about losing the ozone in the stratosphere, which is important because the ozone is protecting us from some of that high energy sunlight. So this was a big environmental concern. And so several countries, not all countries, but a good number of countries got together in 1987 and signed an agreement called the Montreal Protocol to reduce the use of the chemicals that cause the ozone hole. And then this is just a picture of the amount of those chemicals from 1980 to 2100. So this is what would have happened without the agreement, is the black line. The blue line is basically what countries agreed to in 1987. And you can see that the blue line is an improvement. It was a notable reduction in these pollutants that depleted ozone. So this blue line is less, it's underneath the black line, but it's not down to zero in terms of emissions. It actually required a whole bunch of follow-ons to the Montreal Protocol to bring the emissions of these gases down to zero. So the initial agreement was pretty limited in terms of countries and the amount of reduction, but the international community stuck with it with these additional agreements and brought emissions down to near zero. So this is an example where the international community came together and did actually fix a large international problem. There were a lot of complaints at the time that it would devastate the economies of entire countries, and actually economies improved overall. So this is a real success story internationally of what countries can do. So I think this is a cause for hope that we can do something similar with climate change. And it wasn't a stated goal of this agreement, by the way, but the reduction of these pollutants actually reduced global warming by about 25%. So the same chemicals that deplete ozone are also greenhouse gases. So reducing those chemicals actually made it cooler than it would have been. So this actually is also the biggest climate change treaty as well. And then more recently, just last month, the US, again, one of the biggest polluters historically, had a piece of legislation called the Inflation Reduction Act, which, like the first Montreal Protocol, is flawed and limited, but is one of the biggest step forwards legislatively in the US in a very long time, and is estimated, we'll see how well it works out, but the estimate is about a 40% reduction in US emissions by 2030. So in less than a decade, this legislation is aimed at reducing emissions almost by half. So the international community has shown that it can tackle these kinds of problems. And some countries now, including the US, are actually showing some steps in the right direction. So this is not an unfixable problem. We have the tools, we have the technology to reduce fossil fuel emissions. We just need to have the political will to do it. So in general, I think there is a lot of hope, a lot of reason to be optimistic. But I want to end on answering a question that I often get asked, is what can an individual person do? And the good news there is that one of the most important individual actions that can be taken is also one of the easiest. And I don't think this is necessarily obvious, but it's actually really important to talk about climate change with family, with friends, with community. That's actually probably the most important action you can take. Because most people, it turns out, if you survey people in most countries around the world, most people are actually very concerned about climate change, and most people support strong action to climate change, but most people don't know that other people feel the same way. So people tend to say, I personally think this is a big deal, and I think we should have big changes to address it, but I don't think other people feel the same way that I do. So talking about it really can build a community of action. And it doesn't have to be big discussions. Actually, a lot of little discussions, just mentioning it with some regularity, mentioning concern and willingness to action can have a really big impact on these kind of problems. And just my last point, I want to emphasize that almost everything that we might do to address this problem can also solve other problems at the same time. So there are a lot of things that you can do in terms of improving, say, energy efficiency that actually make energy cheaper. So you can actually fight climate change and save money at the same time. There are lots of engineering approaches to improving readiness for severe weather that will help people survive severe weather better in general, not just with climate change. There are lots of policies that can fight poverty. In the US, poverty, homelessness are big issues. People's access to housing, public transportation is a big issue. For instance, where I live, if we improve public transportation, that's more efficient. It'd be a huge impact on climate change. But it also makes it easier for low-income people to get to their jobs, makes it easier for people to access education, and a whole host of other things. So climate solutions are sometimes presented as massive sacrifices, but they can actually, if we think about them the right way, they can also solve a lot of other problems and really benefit a lot of people at the same time. Now, it may be the case that a rich person has to buy one less yacht, but I think that that's probably a sacrifice that we can tolerate as a society. For most people, the majority of people, these climate solutions will actually make their lives better, which I think is important to keep in mind. And with that, again, thank you very much for the opportunity to speak with you.
Thank you so much, Professor Barlow. That was a very enlightening and informative lecture, and I really learned a lot. And I'm also very thankful that you specifically covered the climate impact for the Philippines. Thank you so much. I would like to ask now Ms. Imelda Johnson to introduce our guest reactor for Professor Mathew Barlow's lecture.
Yeah, let me take this opportunity also to thank Matt. That was very, very enlightening. Thanks for showing us the true picture, though it sounds very gloomy, but also you have inspired us in what we can, the steps we can take and when, as individuals, as families, no matter how small, but if you put those small pieces together, we can be a big impact in slowing down climate change. And let me remind people that, as Matt had said, it's a natural process, but also the biggest issue is that the human activities is accelerating the pace of that natural climate change. And in the history of our planet, the 4.5 billion year history of our planet, we've had 5 major mass extinction events. Only one of that mass extinction event was caused by an asteroid impact 65 million years ago. And the rest of them, where we lost at times 92% of species on Earth, were all caused by climate change due to natural processes like volcanism that added greenhouse gases. And still, in the end, that was climate change that did that. And we are confronted with a big problem like right now that every one of us need to take very seriously. And so, friends, the Philippines is a beautiful archipelago of 7,100 islands in Southeast Asia. Every year, it is battered by typhoons. But recently, it has seen its share of super typhoons that has brought significant loss of lives and properties. In November 2013, major news networks from around the world, including CNN's Anderson Cooper, went to the Philippines to cover the devastation of Super Typhoon Haiyan, or known in the Philippines as Yolanda. It was one of the most powerful tropical cyclones ever recorded and took 6,300 lives, the second deadliest in Philippine history. Sadly, the effects of climate change on the Philippines would be significant. To give some brief remarks about this, we invited our friend, Professor Mahar Lagmay, the Executive Director of the Philippines Project NOAA, short for Nationwide Operational Assessment of Hazards. Professor Lagmay is a scientist in charge of disaster assessment, mitigation, and climate change adaptation for the Philippines. Friends, let us welcome Professor Lagmay.
Yeah, hello, Imelda. Thank you. Can you hear me? All right. Thank you very much, Professor Barlow, for your very enlightening talk. Again, I'm Mahar Lagmay of the National Institute of Geological Sciences, and I'm the Executive Director of the UP Resilience Institute. UP stands for University of the Philippines. The UP Resilience Institute is a proactive hub of benchmark innovative information, vital to the nation's efforts in climate change mitigation and adaptation. We have been doing a lot of work related to the country's efforts to mitigate and adapt to climate change. And we can very well relate to what you just said, that the Philippines is at the receiving end of these climate change impacts. The UP NOAA Center, or the Nationwide Operational Assessment of Hazards, which is more popularly known as Project NOAA, was formerly with the Department of Science and Technology and was the government's flagship program for disaster prevention and mitigation, which aimed to create a disaster-free Philippines by providing tools and information to mitigate or avert disasters caused by natural hazards, which because of climate change has been increasing in terms of frequency and impact. Now, the UPRI has Project NOAA as its core component, and it continues to work to help avert disasters, both current and longer term. Future disasters as part of the public service mandate of our university. Over the last century, civilizations have altered the atmosphere through industrialization, and that is what Professor Barlow was talking about. And deforestation so as to cause our climate to change in unprecedented manner. The rapid changes in climate consequently has brought us to experience harsh natural phenomena that threaten populations all over the globe, not just the Philippines, but all over the globe. Climate change consequences, which manifests in records as increased rainfall, higher temperature, more intense cyclones, and rising sea level, impair development of our country and heighten the vulnerability of communities to natural hazards. The Philippines is indeed at the receiving end of the harsh impacts of climate change. We lose about probably about 50 billion pesos per year. And these disasters that have happened eaten up about 3% of our GDP over a period of 10 years. Floods, landslides, and storm surges have become a bane to our efforts to attain the Sustainable Development Goals. Tomorrow evening, in fact, a typhoon, which has just rapidly intensified, will crash into the eastern border of Luzon, the northernmost big island of the Philippines. And for sure, it will be costly to our country. And I would like to take this opportunity, this live Facebook streaming, to get my fellow Filipinos to be aware of this typhoon. It's going to make impact tomorrow. To prepare while there is still time. Particular mention for Central Luzon, the provinces of Pampanga, Bulacan, even Zambales, which is forecast to experience heavy rainfall. Consensus among reputable climate scientists worldwide point to a rapidly changing climate, which needs to be addressed accordingly and in timely fashion. The majority agree that there is a need to stem or slow down the current progression of climate change through immediate and concerted global effort to reduce greenhouse gas emissions and increase carbon sinks. Clean and renewable energy and reforestation are among the suggested solutions. Clearly, the international community recognizes the growing threat of climate change and calls for the immediate adaptive measures to counter its ill effects, to promote resilience of ecosystems and societies. Such adaptive measures must go beyond more technological options that are mainly focused at building infrastructure and other similar measures. The impacts of climate change will not be experienced in isolation, but will affect humans in the context of the way we live. Water shortages for local consumption and agricultural use will affect billions of people. And the risk to natural hazards such as floods, landslides, and storm surge brought by extreme storms will escalate and undermine global efforts to alleviate poverty. Forest fires will become more prevalent, devastating, and more difficult to manage. I believe that in the US, that's a major problem. Rising sea levels will threaten coastal communities where there are dense populations and high-value agricultural lands. Access to affordable food, sufficient to maintain a proper diet, will be limited and threaten food security. These effects are imminent and prompts actions to combat these threats through proper planning by communities that are adaptive and resilient to climate change. The talk of Professor Barlow, entitled Turning the Telescope Back on Earth, the challenges of living on a warming planet, is indeed very, very timely. We need to get more people to become aware. This talk, maybe you can discuss it with your family members and friends and neighbors, for them to be aware of the dangers ahead of us, for us to act now. This forum is one way by which we do this. As an amateur photographer, which I enjoyed doing since, or the hobby since August of 2021, I also enjoyed the highly educational presentation on our planet as explained by Professor Barlow, an astronomer and expert climate scientist, through the discussion of basic, long, and well-established science. So there's really no controversy about it. Majority of climate scientists or scientists all over the world know it and have been warning us for the longest time. So let us listen. Let us listen to what has been said, internalize, because it will all affect us. So thank you very much, Professor Barlow. We really enjoyed your talk. It is indeed very timely, and I hope that everybody who watched this forum will be able to spread the news and spread this concern so that we can all act together to counter the adverse impacts of climate change, and even if possible, work together to mitigate climate change by reducing the burning of fossil fuels and reducing the emissions of greenhouse gases. Thank you very much. Back to you, Imelda.
Thanks, Mahar. That was really, really nice. Both of you have just delivered something that, I hope everyone will take to heart seriously. I was just reading an article that was written a decade ago, published by the American Association for the Advancement of Science, predicting that in 300 years, 3/4 of species on Earth will be gone. And one of the contributing factor is climate change. Jeff?
Oh, hello. Yeah. Thank you. Thank you so much, Professor Mahar. I remember I was much inspired by Project Noah, and I do hope it continues, and you continue with your good work and more power. Thank you, Professor.
Thank
Now
you.
we will go to the Q&A portion. Again, Professor Barlow, there are some questions here that were submitted, and I will read some of them that we can answer. First question here is, when discussing greenhouse gases, everyone talks about carbon dioxide, but nobody seems to mention methane, which is more potent greenhouse gas than CO2. Why is that? I even heard that methane is actually being released now with the melting of the polar ice caps. Is that happening?
Yeah, so that's a great question. Methane is both naturally occurring and as produced by humans, an important greenhouse gas. So I've kind of given a pretty big overview here without getting too much into the details. So carbon dioxide is more important than methane because we produce so much more of it. But that's not to say that methane isn't important. And it is a good point, I think, to acknowledge that carbon dioxide is not the only important greenhouse gas. It's the most important, but it's far away not the only one. And methane is very important as well. Yeah, methane, molecule by molecule, methane is a stronger greenhouse gas. We just produce so much less of it that it doesn't get as much of it, as much attention. But absolutely, it needs to be regulated more carefully. There are a lot of issues with how methane is produced. And then, as you mentioned, there's also large reservoirs of methane in the natural ecosystem that are currently frozen. And there are concerns that in a warming planet, that naturally occurring methane might melt and be released into the atmosphere and reinforce existing climate change. So yeah, methane is definitely important.
Thank you, Professor. In relation to this question, when calculating the amount of greenhouse gases that are causing global temperatures to increase, do you also take into account those produced by volcanic eruptions and wildfires?
Yeah, so that another great question. So volcanoes do produce greenhouse gases, and they also produce particulate matter that reflects sunlight. So volcanoes can warm and cool the climate, and big volcanoes have substantially cooled the climate for a year or two at a time. So on the time scale of a year or two, volcanoes can be very important to the climate, but humans emit much more than volcanoes on average. So that is absolutely accounted for. And year to year, it can be important, but in terms of trends in the climate, what humans do is much more than volcanoes. And the other one is fires. So one of the biggest, fires have a number of impacts, but one of the biggest impacts of fires on the radiative balance of the Earth is that the soot falls on snow. And fires are big enough now that the soot from fires can get all the way to the Arctic and the Antarctic. They land on the snow, and this is true in high mountain Asia as well. They land on the snow and it's not as white as it was, and it melts more rapidly. So particulate pollution from things like fires actually contribute substantially to snowmelt around the world. So those things are definitely accounted for. It's not always easy to accurately account for them. And one of the challenges in getting some of the numbers right is that we need to be observing many properties of the Earth all over the Earth, which is pretty expensive, and countries have also not been quite so keen to fully support. But those factors are definitely accounted for, but we have a fair amount of uncertainty in them right now, I think.
Thank you. In relation, this question is closer to home in relation to climate impact for the Philippines. Is the Pacific Ocean experiencing a La Nina event right now? If it is, what are the potential effects of La Nina on the Philippines and the rest of the world?
We might have other folks on the call who can better than answer the Philippine piece. So we are entering a La Nina right now, which is the third La Nina in a row, which is pretty unusual. That has a lot of effects all around the world. Exactly how it affects the Philippines, I don't know if anybody on the call might actually have a better sense of that. It does tend to make the Western Pacific warmer than average, which is probably bad news for typhoons, but I don't actually know the exact answer to that. Does anyone else?
Yeah, I think I can answer that. You mentioned that we have a La Nina now. Well, that's opposite to El Nino. If we have El Nino, the effects to the Philippines will be more severe droughts, in particular. When you have La Nina, the effect in the Philippines would be to have more rains. So this year, I don't know, I haven't measured it yet, but climate-wise, I mean, long-term, the effects of La Nina to this part of the world, particularly the Philippines, would be to increase the rainfall amount.
Thank you, Professor. I would like to read now, I think these two questions are related from our chat. First, this question goes as follows. I have read that what humans are doing are not related to climate change because climate change is part of the Earth's cycle. What is your opinion about that? Are humans really responsible for climate change, or is it just a period of the Earth's cycle? That's the first question.
Yeah, so that's an easy question. And that goes back to the kind of highly paid disinformation campaign from fossil fuel industry. Humans are absolutely changing the climate in pretty dramatic ways. The climate does also vary a lot on its own over long time scales. So the climate does change. We have ice ages over the last few million years. But just as one point of reference, the average difference in temperature at the surface of the Earth between the ice age, the last ice age, and now, so 20,000 years ago, where I am right now would be under a kilometer of ice, the world was only about 5 degrees cooler Celsius. And humans have caused 1 degree of warming Celsius in just the last 100 years. So it is true that the Earth's climate does vary naturally, but the Earth's climate varies by several degrees over tens of thousands of years. And the effect of humans is already more than a degree over less than 150 years. So there are both kinds of variability, but the human one is very large and very fast relative to what's occurring naturally.
Thank you, Professor. I said there's a related question, and I'll read it. The Earth regularly goes through cycles of heating and cooling, and we are currently in the cool stage as we have polar ice caps. And the normal stage of the Earth is not to have any polar ice caps. What is your opinion on this?
Yeah, so
he said, yeah.
Oh, sorry. So there are natural cycles in our modern climate, the climate of the last million years or so, where we cycle back and forth between more ice on the surface, called ice ages, and periods where there's less ice. If there weren't human impacts, we would be headed probably back towards the more ice phase of things. But we quite possibly have cut that cycle off because it's so much warming. So that cycle does occur naturally, but the scope of our warming, human-caused warming now, is probably enough to actually interrupt that cycle. We won't be losing our ice at the poles anytime soon. It might, and in fact, probably completely melting the poles would take thousands of years. But if we melt all the ice from the poles, the ocean sea level would rise by, actually, I forget the exact number, but 100 meters, 150 meters, or something like that. There's a vast amount of water at the poles. If we melt even a tiny fraction of that, which is what we're doing now, we'll get sea level rises that will dwarf anything that we're looking at currently. And the Philippines are an island nation, but most of the population of the whole world is close to the coast. So melting any substantial part of the polar ice caps will have just massive changes to the whole global landscape.
Thank you, Professor. Now we have a question about some measures that we can do to mitigate climate change. The question is, how much impact to climate change is the conversion of vehicles from gas and diesel to electrically powered? Will it really matter?
Yeah, I think the answer, again, I don't have the numbers off the top of my head, but the answer is that it will matter a lot, both because cars around the world directly emit a lot of carbon dioxide when they run. So if you switch to an electric car, then you're running on electricity. But how is that electricity generated? If you have electric cars, you can then more easily generate runoff of electric energy, which you can then generate with renewables. So switching to electric cars is a piece of the solution. But using public transportation, which is a huge issue in the US, we're not very supportive of public transportation. Public transportation is a much more energy efficient way of moving people around and is usually much more equitable. It's much more accessible to low income people. And it's much more environmentally friendly because you're not taking up all the space of cars. So it is very important to switch to electric cars. That is a very big deal. But it's probably even more important to switch when possible to much more public transportation, which is just much more efficient and much more environmentally friendly. If you think, if you ever walk around a city and look at the space that's taken up by streets and parking lots, it's just amazing the amount of space that we've dedicated to cars, particularly in the US, that we could move the same people with just a fraction of that space in public transportation.
Thank you. This question is different. It's from the perspective of planetary science. And this is an interesting question. If we were to introduce more greenhouse gases into Mars as part of the plans to establish stations on Mars, would we be able to create a more tolerable environment closer to Earth?
Yeah, I'm a little bit out of my area of expertise on this, but I know that people have actually thought about this very carefully. The short answer is yes. If you introduced a greenhouse gas atmosphere to Mars, it would even out the temperatures. It's really hot during the day and really cold at night. So you would even that out and make it more habitable. Exactly how you would create that atmosphere, that's a lot of mass that you either have to move to Mars or get out of the Martian surface. It would be very hard to keep that atmosphere, to make that atmosphere in the first place. And I'm not entirely sure that it would keep that atmosphere. But I'm not enough of a Mars expert to be able to say. I know people have speculated about that, but I don't know actually what it would cost to try to do something like that.
Thank you. Let me go back now again to Earth. Can you say something about climate migration and climate refugees? Climate migration and climate refugees.
Yeah, so that's a great question and one of the major concerns. I think one of the things we try to stress with climate impacts is that it's not just what goes on right near you in the US, we say, right in your backyard, that's important, because we're a global society and things that happen on the other side of the world matter to us. COVID, I think, probably drove that home. So when you have massive impacts in other parts of the world, people move in response to that. And then those people ideally have to be humanely accommodated. But just as for instance, in Pakistan, the flooding this summer displaced, estimates are in the millions of people were displaced within the country because of that. So climate migration, people moving within a region because of climate impacts is a huge deal, but also people moving between countries. For political reasons, I think globally countries are really struggling with immigration without climate change, but climate change will certainly exacerbate those issues of migration. And a lot of island countries, I think some of the smallest islands will become uninhabitable, and those people will need to move somewhere else. So it's already a big issue, and it will become a bigger issue.
And Professor, related to that question, I've been hearing that there is reverse migration away from Florida, which they're saying will continue to sink as water levels rise due to climate change.
Yeah, Florida's a very low-lying state, but it's like large sections of the state aren't going to go underwater for hundreds of years at the earliest. But coastal Florida, the areas around Miami and like that, there is a lot of coastal flooding, and Florida has not really dealt with that. So there is some migration around the coast, but there's also still a lot of coastal development, even in areas that regularly flood now. So I don't think that there's been a sort of a realistic response yet to the risk of buying a property, say, in the coast in Florida. Those properties still sell pretty well, even though they are going to be flooding more regularly. So I'm not sure that that's become an issue yet. It will become an issue, I think, much more over the next few decades. And then politics, as always, really comes into this. And Florida, a few years ago, scientists weren't even allowed to use the phrase climate change in any official Florida document. So it's been very hard to talk about. But even in Massachusetts, I think we're starting to struggle with that. But if we have a lot of very well-off people who live on the coast, and they can just sell their property. But we also have a pretty a lot of low-income neighborhoods, and it's very hard for them to sell their homes on the property. So it's not easy, I think, to move away from the coast for most people. But that is a sort of oncoming tragedy or issue that I don't think we've really wrestled with yet, at least in the US.
Thank you, Professor. And this is another question. Could Professor Matt address composting as another individual action to mitigate climate change? Yeah, composting.
Yeah, that's a great topic. And I think there's two ways to think about personal issues like composting. One is that, yes, it is helpful, and composting provides a lot of benefits. It also reduces waste, food waste, and the amount of garbage in landfills and stuff like that. But we need to do sort of two things for climate change. One is we need to take some personal actions that reduce our kind of personal impact, but the changes we really need to see are at the government level and the international level. So and it's not a choice, but if it were a choice between doing a little more composting and talking to your neighbors about the political importance of climate change, it's probably talking to other people is maybe one of the most important things that you can do. That said, I mean, composting is helpful, but even in my own family, we used to compost ourselves. Well, we ourselves used to compost. We didn't compost any members of the family, but we used to do composting on our own, but then we now pay into a service that picks up our compost separately from the trash. And that's just a more efficient way. Unless you live on a farm, it's actually much more efficient to be part of these systems. So individual action is helpful, but what we really need are these kind of large systemic changes, changing the systems of how we do things a little more than what we're doing individually. That said, many people have probably heard the term carbon footprint, which is, you know, what you yourself do in terms of carbon emissions. What's more important now, people like to talk about your carbon shadow, like the influence you can have as an individual on other people and systems. So if you're interested in composting, getting your town to compost would be, the time spent on that probably would be, you know, much more effective than the time you might spend composting individually.
Thank you so much, Professor. Thank you again for this, for your lecture and for your advice to us, because I really learned a lot about, especially how to, as an individual, to help solve this problem, which is really affecting all of us. Before we end the Q&A, maybe I could ask our other attendees, our other panelists, if they have questions for Professor Matt.
Jeff, I do.
Yeah.
Matt, if you could address, as you mentioned earlier, the United States is the biggest contributor to this problem. And aside from automobiles, you know, Americans are obsessed with lawns. And every week you hear lawnmowers, gas-powered lawnmowers, gas-powered lawn tools going on and on and
Leaf
on.
blowers.
And leaf blowers, and, you know, just all gas-powered. Recently, we converted to electric, battery operated. And also we have talked to our neighbors to doing the same, and they have done the same thing. I mean, that's a small step, right? But also nitrogen fertilizer. I heard somewhere that the nitrogen fertilizer we feed our lawns is a big contributor to climate change. Can you kind of explain to us a bit more?
Yeah, so let me just start by saying that historically the US has produced the most carbon. It's not actually the most carbon producing country at the moment. So just to clarify that point. So going forward, it's the big population countries like China and India that are producing the most carbon. But the US has produced the most carbon. In terms of lawns, I would have to think a little bit about the climate impact of lawns. The water and the pollution impacts of lawns, as you say, are massive because of the fertilizer, which then runs off into the water system. A lot of pesticides are typically applied, which are busy killing off our insects, which is another huge problem. And lawns require an epic amount of water. And access to fresh water is a huge issue around the world. So I don't off the top of my head know the climate impacts of lawns, but it's certainly fair to say that from an environmental, a water, an ecosystem point of view, lawns are absolutely a terrible idea. There's a whole movement called de-lawning now in the US to try to encourage people, particularly in the West, where water access is a huge issue now. But for a large number of reasons, lawns are a really poor idea. And yeah, I think that's worth stressing. And especially in terms of water usage, which does tie back into climate change, converting a lawn to native local vegetation is I think probably one of the bigger steps that one could do on one's own property. So it's not a small thing to get rid of a lawn, for sure. And if a lot of people did, it would make a pretty substantial difference environmentally, at least.
Okay, another one, Matt, talking about water. I attended a talk at the university where one of the professors talked about saltwater intrusion and the effects on infrastructure. And one of the examples he gave was the condominium that collapsed in Florida. Now, is that something that, countries like the Philippines should be very concerned about because there are big condominiums along the waterfront?
Yeah, and I'm not an engineering expert, so I want to just put that out there first. But yeah, you're absolutely right to highlight that, I think, as a really critical issue at the coast. So as sea level rises, the mix between fresh water and salt water in the ground right near the shore changes more towards salt water. And so if you have building foundations, many, not all, but many types of building foundations are sensitive to salt water. So as you get more salt water with sea level rise, that can corrode the rebar, the steel inside the cement, can actually destroy some of the cement. Even just a changing in water level can impact foundations pretty substantially. So for sure, there are a lot of foundational issues, structural issues associated with sea level rise at every coast that are a big deal. I couldn't speak to the Philippines exactly. For that matter, I don't think I could speak to Boston even exactly, but it is definitely a major concern as sea level rise, what that does to the foundations of buildings at sea level.
Jet, unless somebody has a question, I'd like to pose my question to Matt. Matt, in one of the slides you showed us earlier, you showed the difference between Venus and the other terrestrial planets. Its greenhouse gas effect the greenhouse effect is much stronger than the other planets. Why did Venus become such a condition like that? Yeah, it has a runaway greenhouse effect.
Yeah, I'm going to disappoint you with my answer. Is that I don't think I know enough about Venus to do a good job of answering that question. But as the planet got warmer, more carbon dioxide came out of the planet's system, and then the warmer it got, the more carbon dioxide you got. Then that makes it warmer, which brings in more carbon dioxide, and eventually you get this massively dense atmosphere that has that huge greenhouse effect. But in terms of like the geologic processes, I'm afraid I don't know enough about Venus. But for sure, Venus is fascinating to people since the early 1900s for exactly that reason, to try to figure out how it came to be the way that it was. Because I think there are some suggestions that originally it had water on its surface. So originally it had a surface temperature more like that of Earth, and then it spun out of control for ways that, again, off the top of my head, I don't know. I think one question that people have wrestled with is, can that happen on Earth? How much should we be concerned that as we're warming the atmosphere, the Earth gets a runaway greenhouse effect? And that part I can answer a little bit, is that the current thinking is that we are not anywhere near triggering that kind of a runaway effect anytime soon. In fact, it's not entirely clear it's possible on Earth, but exactly that process, I should probably go look that up because it is so fascinating. But off the top of my head, I don't know. But yeah, Venus is just an amazing planet. And as you probably know, they've a few times dropped probes directly onto the Venus surface to try to measure things, and they have measured those surface temperatures. But the atmosphere is so massive and so corrosive that the probes just last a few hours, I think.
Thank you. Professor Mahar, do you have a question for Professor Barlow?
Yeah, just a follow-up question. You mentioned about probes. So the difference in the measurement of the surface temperature and the atmosphere of the planets Venus, Mars, and there was another planet that you put in the table. Those are measured, the surface temperatures are measured with actual instruments, or they are remotely measured?
So originally they were remotely measured, and you can do it all with remote measurements. Now, I think Mercury was the other one. Now all of those planets at this point have been measured in situ, with probes. But when those original calculations were done, they were all remotely measured. We can pretty accurately in our own solar system, I think, measure the surface temperatures just by the planet emissions.
Thank you.
Thank you. Any other questions from our panelists?
Yeah, I'd like to toss out one question. With the adoption of electric vehicles and solar-powered homes with battery backups, I know and this is probably part of the disinformation campaign regarding batteries, because there are those who say that because the current battery technology requires rare earths, which the mining of these rare earths also can have an environmental impact. I'm actually a battery vehicle enthusiast, and I know that I believe that in the long-term effect of running electric vehicles or solar-powered homes should more than make up for the environmental impact of mining. And I was just wondering if Professor Barlow can address naysayers regarding battery technologies and the impact of manufacturing these batteries.
Yeah, I think that's a great point. Any energy production and energy storage method has negative impacts, right? And I think you're right that is important to talk about, because it has been used also to kind of dismiss these technologies. So it is absolutely true that modern batteries require rare earth minerals, and that mining those, any kind of mining has environmental impacts. I think the point is just that every type of energy production and storage has environmental impacts. What you need to do is assess them and then compare them. I think if you look at the overall environmental impact of those kinds of mining, it is negative. Those mines do have negative environmental impact. It's just much, much, much less than all the negative impacts associated with fossil fuel production, which also involves, mining or drilling of some sort, transporting things, in addition to all the climate change implications. So I think the engineers refer to that sometimes as life cycle analysis, where you try to look at the overall impact of something environmentally. So yeah, it's my understanding that the benefits for the case of electric batteries vastly outweigh the costs. But it is, I think, important to acknowledge that all these things have costs. The same thing is true for solar panels. You have to do some mining to get what you need for the materials you need for solar panels. Solar panels are not super easy to dispose of in a environmentally friendly fashion. So there are environmental impacts to solar. There's environmental impacts to wind. One thing that always comes up is they do kill some birds, which they absolutely do. Nuclear has the waste disposal problem. If you have hydropower, damming up rivers is actually a significant environmental issue. So every form of energy production and storage has environmental impacts. The key, I think, is to count them up and then compare them. And yeah, I agree with you that to my knowledge, the benefits vastly outweigh the costs for current electric batteries, but they do have a cost, like everything does.
Thank you. Imelda? Edwin? We're good? Thank you so much, Professor. Now let me allow me to take this opportunity to present you our token or certificate of appreciation and from the Astronomical League of the Philippines. And I would like to read the certificate. It mentions that the certificate is presented to Professor Mathew Barlow for his invaluable insights, experiences, and expertise shared with the participants of the webinar entitled Turning the Telescope Back to Earth, the Challenges of Living on a Warming Planet, held as part of the ALP Astronomy Experts Series 2022, given this 24th of September, 2022, signed by President James Kevin T. and Vice President Jose Francisco Aguilar. Thank you so much, Professor. We will try sending you a physical copy of this certification as well.
Thank you so much.
And,
It's been an honor to speak here and a real pleasure. Thank you.
Yes,
Thank you.
Professor,
Hi.
it's time for us before we
Group shot.
let
Group
to
shot.
go to have a good group shot.
Okay.
Of course,
I'm-
with Professor Mahar as well.
Okay. You ready? Andrew, ikaw lang ba? Andrew? Ready? Andrew. 1, 2, 3. One more. 1, 2, 3. Isa ba? 1, 2, 3. Okay.
Oh, that's
Thank you.
Casey.
Thank you very
Yeah,
much. Thank you, Professor Barlow, for accepting our invitation to be our speaker. Thank you.
yes,
And
thank
also
you so much.
Professor Mahar.
Yeah,
Also,
thank you so much,
Professor Mahar Lagway. Thank you.
So thank you so much, Matt and Mahar, for your generosity in sharing your time and expertise with the panel and all the viewers and attendees of the webinar. Thank you so much. We appreciate it.
Yes.
Thank you, sir.
Thank you very
Thank
much.
you very much.
Professor
very
Barlow,
much,
you mentioned
Professor.
that we can have a copy of the presentation as PDF. Would that be okay?
Yes, I will definitely send that. I'll send that
Okay.
now.
Thank you.
Thank you so
Thank
much,
you.
sir.
Professor Barlow.
Thanks.
Thank you.
Thank you.
Thank you also, Professor Lagmay, for joining us. Thank you.
Thank you. You're welcome.
Thank you.
Yeah.
Bye.
I would just like to continue present something before we end. Let me share my screen again. So as like our president James mentioned, this is actually our 8th webinar in our ALP Astronomy Expert Series of 2022. And of course, Professor Barlow is the last one so far. And we would like to express again our profound gratitude and thanks to all our webinar speakers who have very generously shared their precious time and knowledge and expertise to us, the World Amateur Astronomical Community. And we can never thank you enough for that. And we would also like to inform you that all of these lectures will be available in YouTube in our ALP YouTube channel. So these are all recorded, so you can view it on demand if you missed today's webinar or the past webinars. And lastly, before we end, I would like to make the announcement for our upcoming speakers. So for October, the final date to be announced is we will have our noted world-class, world-famous amateur astronomer, Adam Black, to speak on astrophotography, followed by in November by Scott Roberts, who is the founder and president of Explore Scientific. And for December, we have a very, very interesting talk by Father Christopher Corbali, SJ of the Vatican Observatory. So this is the poster teaser from Adam Black. He will be talking about the human equation in astroimaging, and the exciting lecture on the Star of Bethlehem. What is really the Star of Bethlehem? to be given by no other than Father Christopher J. Corbali, SJ of the Vatican Observatory. Wait for further announcements. Visit our website, astroleaguefields.org, and we will also be announcing on Facebook these upcoming webinars this October, November, and December. So thank you very much. Take care, everyone, and clear skies always. Again, for all our panelists, we will be having a webinar meeting after this.
Thank you.
Thank you.
Yes, thank you
Thank
for
you,
attending,
everyone.
everyone.
Thank you. Bye-bye.
Mahar,
Bye-bye.
I will be calling you.
Bye-bye.
Yes,
Bye-bye.
bye, everyone.
Thank you.
To all our
Thank you,
attendees.
Professor Mahar. Thank you.
Bye-bye.
Thank you.
Bye, Professor Mahar.